Hello everyone. In this lecture, I'll be discussing the correlation between the 18 electron rule and the molecular orbital theory. So what does the 18 electron rule say? The 18 electron rule says that any coordination complex will have 18 valence electrons, will tend to have 18 valence electrons. That will be its most stable state. This is what we know. But it's not necessary that only those complexes are going to be stable which are 18 electron. It actually depends on the type of ligand it has. It depends on the type of molecular orbitals energy profile diagram it has. How much is the interaction happening? How much is the splitting occurring? It depends on that also. How? We'll see. So let's say okay, so we can categorize the ligands. So in all the cases we are considering only octahedral complexes. So we can categorize the ligands into three broad categories. First is having weak sigma interaction and weak pi interaction. So if you could recollect from the molecular orbital theory of octahedral complexes, especially for the sigma bond, you would know that you have the orbitals, T2G orbitals, followed by the EG, A1G, and T2G star. Okay, right? I mean, all of these are antibonding. This is the non-bonding. So when you have weak sigma interaction, so that would mean the bonding molecular orbitals are stabilized less, and at the same time the antibonding molecular orbitals are destabilized less also. Destabilized less means their energy is not increased significantly, the energy is not increased very much. So that would mean this splitting is small, and if splitting is small, you have let's say it should be something like this. Yeah. So these are filled by the ligands. So you have 12 electrons here, 6 electrons here, and if the splitting is not very large, if the splitting is less, extra electrons which may be present on the metal can actually occupy these, and you can have +4. So you have 12 to 22 valence electrons possible for these kind of complexes where the ligands have weak sigma interaction, weak pi interaction. So in these kind of complexes, 18 electron rule is not necessarily valid. It may be valid, but it's not necessary that these complexes will also always obey 18 electron rule. Okay. The second case would be it has strong sigma interaction, weak pi interaction. So we are still focusing on the sigma bonding. Now in this case, if it has strong sigma interaction, that would mean the bonding molecular orbitals are stabilized more, the energy is decreased more, and the antibonding molecular orbitals are destabilized more, their energy is increased more. So that would mean if this is your non-bonding, this will be your EG. The splitting has now increased. Now since the splitting has increased, I'm explaining here only. So the 12 electrons will obviously be filled by the ligand group orbitals, ligand electrons, that's fine. 6 electrons will be filled here, so you have 12 plus 6. Now these orbitals out of bound at room temperature to be filled by the metal electrons. So you have 18 electron rule satisfied in this case, depending on if it has the metal has 6 electrons available, let's say. So it will have 12 to 18 electrons count. So these are those complexes which are likely to follow the 18 electron rule. The third category is having strong sigma interaction and strong pi interaction also. So this case is not very much different from the second one. So when it has strong sigma interaction, we already know that the EG star is already very high up in energy. So you have this T2G non-bonding orbitals and you have strong sigma interaction. We are taking the case of X sigma acceptor. So you get this to be something like this. I'm not going for the anti-bonding. And then you have the EG star here, because obviously the splitting is large because of the strong sigma interaction. Now the splitting is even higher. So it's literally not possible for the metal to access the higher energy levels to fill up their electrons. So here also it is going to follow the 18 electron rule. Okay, so yeah, so these are the three broad categories of ligands, and these are the three broad cases that you can have wherein even if you consider the strong sigma interaction, weak pi interaction is not going to change because the splitting is already very high. So these are the three cases of 18 electron rule explained with the help of molecular orbital theory. And now this is not important from the examination point of view, but this is some aspect of molecular orbital theory that you should know in correlation to 18 electron rule. I found it interesting to discuss. Oh, by the way, this has been taken from R.P. Sarkar, Inorganic Chemistry, Volume 2. And they have actually given a detailed explanation to this approach, 18 electron rule from molecular orbital theory, and also to molecular orbital theory for all kind of complexes, whether be it tetrahedral, square planar, or octahedral complexes. So by now we have actually created the basis for our discussions in the coming lectures. Now we'll start the discussion on the applications of molecular orbital theory for coordination complexes, wherein we'll start with color and electron spectra, from which questions have come a lot in all kind of exams. It is a very hot topic. So in case you have any difficulty or any query in the discussion so far, you can always put them down in the comments. I'll try to again discuss it or again clear them up in the comments or in the coming lectures. In the next lecture, we'll start with the color and electronic spectra.